This is a supplementary video for our paper detailing CusADi, our framework to parallelize expressions on the GPU with applications for optimal control. One of the main results of our work is approximating MPC so that it can be evaluated as a closed-form expression, as seen in the background. With CusADi, we can parallelize this controller across any number of environments, which we do here with NVIDIA's IsaacGym. The motivation for this work stems from how model-based techniques can complement reinforcement learning. By implementing model-based techniques into an RL training loop, we expect to see improvements in sample efficiency, exploration, and the interpretability of our policies. Of course, these model-based techniques aren't limited to MPC. Reduced order models, dynamics algorithms, and so on could all be ported into training environments. There's a breadth of work studying how to combine the two effectively. However, a major bottleneck has been in the implementation and scalability of these model-based techniques. It's complex to implement algorithms for tensors of data, it's hard to solve optimizations efficiently for thousands of agents, and there's significant overhead from passing data between the CPU and GPU. To address this, we present our work CusADi. CusADi extends the framework of CasADi and combines it with the parallelization of CUDA. Here, we have a simple function, which is expressed in CusADi's symbolic language. CusADi represents these functions as an expression graph. The function is computed by iterating through each instruction, I1, I2, and I3, and performing the specified operation on scalar values. Even for matrix expressions, the operations are broken down to operate on scalar elements of the matrices. One advantage of using GPUs is large-scale vectorization. Instead of adding individual scalars, GPUs can add tensors of data together as a single operation. The key insight behind CusADi is that we can vectorize each operation in the same way with CUDA. By doing so, we can evaluate the original function in parallel across huge batch sizes by leveraging all the threads available on the GPU. CusADi programmatically generates CUDA kernels that can be compiled and used with PyTorch. For benchmarking, on the left, we show CusADi speedups relative to serial CPU evaluation for 5 different functions, each containing 10 times more instructions than the last. On the right, we include the overhead from transferring data between the CPU and GPU, and we see speedups of up to 10,000 times depending on the application. To parallelize MPC for the MIT humanoid, we implement the controller from Hong et al. In CusADi. One limitation of GPU parallelization is that all the operations are computed in lockstep, making it challenging to implement algorithms with conditional flow. For MPC, if the controller for one environment converges faster than another, there's no efficient way to pause evaluation and continue the computation for the other environment. To address this, we implement a custom symbolic solver and strictly fix the number of iterations in CusADi. When we plot the Pareto curve of cost and constraint violation against computation time, we can clearly see the trade-offs for this system. The marginal benefit of solver iterations decreases rapidly past around 5 or 6 iterations, suggesting the controller can perform well even with early termination. And when we visualize these approximations in simulation, we can likewise see little difference in performance between 5 and 20 iterations. Subsequently, we can evaluate this MPC across thousands of environments in IsaacGym or IsaacLab. While we leave training a policy with MPC to future work, a PPO iteration takes roughly 3 to 4 seconds when running the MPC and policy at 100 Hz, while the simulation runs at 1000 Hz. Instead of MPC, we can also parallelize useful algorithms or quantities from the model-based literature. Shown is an efficient algorithm for computing the centroidal momentum matrix derived by Wenzing et al. By using it as a task in a whole body controller formulation, the work shows natural arm swing behavior for a kicking task. We take the CusADi implementation of the algorithm and compute it in parallel for the MIT humanoid. By rewarding a desired centroidal momentum instead of just the base angular velocity, we see emergent arm swing behavior from our locomotion policy. For our final application, we look at using CusADi for parallel simulation with a planar quadcopter, subject to thrust limits and with an attached LQR controller. In CusADi, we can represent and embed the drone dynamics, the LQR controller, and the integration for a simulation step as a single function. Additionally, we can define the function with the parameters of the LQR controller, phi LQR, and the system dynamics, theta drone. Now, suppose we have some nicely tuned controller that we want to characterize. Specifically, let's say we're curious how well it can handle disturbances and from what states it can recover. With CusADi, we can evaluate our function for tens of thousands of quadcopters and forward simulate our system to see how it performs. We simply need to initialize z0 to a wide range of angular and linear velocities. When we roll out these samples, we can easily visualize the region of attraction for our controller and approximate it with some convex hull. While this example is trivial, we can imagine doing the same for a whole body controller for a legged robot and estimating when it is able to stabilize and when it needs to take another step. Another scenario we can consider is for tuning, sensitivity analysis, or system design. In other words, how does any parameter of our system, the weights, the masses, or the limits, affect our resultant trajectories? This time, we can sweep the values of phi and theta across a wide range to see their effects on trajectories. Instead of tuning controllers iteratively, CusADi makes it easier to look at the global effects of parameters like the LQR weight on X for the left plot, the LQR weight for the inputs in the middle plot, and the mass of the system for the right plot. We can directly see the sensitivity of the optimal trajectory from each of these parameters, and tune our controller based on our desired trajectories or state constraints. Of course, these examples aren't exhaustive. There are several ways we're thinking about extending CusADi, both as a tool and for robotics applications. One interesting direction is to begin tackling high-dimensional estimation problems, where we can generate massive amounts of data with CusADi to estimate things like the value functions from MPC rollouts, or do value iteration on reduced order models or learned latent dynamics. Another potential direction is to leverage this kind of parallelism for online controller adaptation. Sampling strategies could be used to better estimate system parameters or perform online domain randomization with belief priors of the environment. Thank you for listening, and please feel free to look at our repository for CusADi or reach out to me with any questions.